Hello everyone, welcome to Module 8.4 of the GPU Teaching Kit. This lecture covers the analysis of data reuse in tiled convolution. The objective of this lecture is for students to learn to analyze the cost and benefit of tiled parallel convolution algorithms. The students should learn that there are more complex reuse patterns than matrix multiplication because the input elements are not reused in a uniform way in the shared memory. This slide shows a simple example of 1D convolution with 8-element output tiles. And we see that for the calculation of the 8 output elements, we need to load 12 input elements into the shared memory. And each output P element will use 5 input N elements. We show that for element 8, we will need to use input elements 6, 7, 8, 9, 10. For output element 9, we need to use input elements 7, 8, 9, 10, 11. So every output element will be accessing 5 input elements without tiling. So a very simple way to calculate the tiling benefit is, for this example, is to say that we are going to load 8 plus 4 input elements into the shared memory. So we have a total of 12 global memory accesses for loading into the shared memory. And then in the untiled version or non-tiled version, we will have 8 output elements, and each one will be doing 5 global memory accesses. So there are 40 memory accesses that are replaced by shared memory accesses. So we converted the original 40 global memory accesses into 12 global memory accesses into the shared memory. So this gives us a bandwidth of reduction of 40 over 12, which is 3.3. In general, for a 1D tiled convolution, we will need to load the width of the output tile plus mask with -1 elements into the shared memory. And in the non-tiled version, we would have access global memory output tile width times mask width times within that tile. So this gives a reduction factor of the two quantities. And this calculation ignores the ghost elements for the leftmost and the rightmost thread blocks. There's another way, perhaps a more complex way of looking at the reuse. Whenever we load the input tile into the shared memory, each input element will be reused a number of times when calculating the output tile element. In this example, N6 is only used by the calculation of P8, but N7 will be used in the calculation of output elements P8 and P9. So element 6 will be used only one time, and element 7 will be used 2 times. Element 8 will be used 3 times. Element 9 will be used 4 times. After that, element N10 will be used 5 times, and all the way through element 13. But after that, N14 will be used only 4 times, N15 will be only used 3 times, N16 will be used 2 times, and N17 will be only used 1 time. Now that we know the number of times each input element will be used in the shared memory, remember that each use of the shared memory eliminates an original global memory access. So from our previous slide, the number of times that each element is accessed is 1, plus 2 plus 3 plus 4, and then we have several elements that are reused 5 times. So it's 5 times a minus 5 plus 1. And then we have 4 times, 3 times, 2 times, and 1 time for the trailing elements in the input tile. If we add up all these numbers, we get 40. So the total reduction is the 40 global memory accesses that were replaced by shared memory accesses divided by the initial 12 global memory accesses needed to bring these data into the shared memory, and this also gives us the number 3.3. In general, if we look at it from the input element reuse perspective in the shared memory, we would have a series of 1 plus 2 plus all the way to mask width minus 1, and then we have a series of elements that will be reused mask width times, and the number of these elements is the width of the output tile minus mask width plus 1, and then we have a trailing series of mask width minus 1 down to 1. If we add up all these numbers, the series, we will get a mask width times output tile width. So the total of output tile width plus mask width minus 1 input tile elements, we will be able to eliminate mask width times output tile width global memory accesses. Therefore, the ratio of these two give us the same. This slide illustrates the importance of tile size with respect to the memory reduction, bandwidth reduction. In the table we show for 2 different mask width 5 and mask width 9. We show the reduction ratio for different output tile width. We start with output tile width 16 and we end with tile output size 256, and the students can calculate 512 and 1024. For mask width 5, the reduction ratio starts with 4.0 with output tile width 16 and ends with 4.9 for output tile width 256. As we can expect, when the output tile's width is much bigger than the mask width, we essentially should have every element to be reused about 5 times. That is, the middle section of the input tile, where every element will be used 5 times, is much bigger than the elements that are on the edge of the tiles. So that's why as we increase the output tile width, the reuse ratio approaches 5. When the mask width is 9, the reuse should approach 9, but the fact that the mask width is bigger means that the output width needs to be even bigger in order for the middle section to be much more significant than the edge sections. So that's why we needed to have bigger output tile width in order for the reuse rate to approach 9. For 2-dimensional convolution tiles, the calculation is actually quite straightforward. It's just the square of the 1-dimensional case. So essentially, we have output tile width plus mask width minus 1 square input elements that we need to load into the shared memory. And then for the calculation of the output elements, we have, the output elements need to access mask width square input elements, and there are output tile width square output elements in the tile. So if we take the ratio of the total number of output elements times the total number of global memory accesses and divided by the total number of input elements in the input tile, we get the ratio of the global memory reduction that we're showing in the bottom of the slide. So we can plot the same trend of memory access reduction ratio given a mask width and given an output tile width. Keep in mind that now that we have two dimensions, the output tile width will need to be smaller because the shared memory now needs to accommodate the square of the output tile width and input tile width, and also the number of threads in the the thread block need to accommodate the square of these numbers. So so for the output tile width of 8 through 64, we see that the mask width of 5, the reduction ratio would increase from 11.1 to 22.1. And we know that the number of reuses, if the output tile is much bigger than the mask, then it should approach 5 squared, which is 25. But in this case, because 64 is not significantly larger than 5, sufficiently larger than 5, so it is still going to be 22.1 rather than very close to 25. And for the mask width of 9, the ideal reduction ratio should be 81. But for tile size, output tile width of 64, this is actually 64 times 64 elements in the output tile. We only will have 64 ratio, which is not quite close to 81 yet. This means that shows that the tile size has significant effect on the memory bandwidth reduction ratio, and that's the reason why there's always a pressure for the GPU vendors to increase their shared memory size so that they can accommodate bigger tiles and therefore achieving higher memory bandwidth reduction ratio. This concludes Module 8 of the GPU teaching kit. Thank you.